This is called crystal field theory for coordination compounds or of coordination compounds. One thing is that it is an electrostatic model. This is an important thing. This is the starting point, in fact, for this crystal field theory. This is a starting point that it is a electrostatic model. When we say electrostatic model, you immediately think that the kind of bonds that we are talking about, they are ionic in nature. They are considered ionic in nature. Okay, you may ask the question, how can we consider? Does it exist or not? That's the question you should ask, right? It's always the starting by consideration. Then we prove experimentally or theoretically, and then we justify that that is how it exists, right? So this is a starting point. See, in previous theory, you remember, it was a pure consideration of covalent bonding. Valence bond theory was all about VBT was all about covalent bonding, because in that theory you were talking about, you remember, the hybridization of the orbitals of metal orbital and then the overlapping of metal orbital. Let's say there is a metal orbital and overlapping with the ligand orbital. Okay, whatever it is, they are overlap, and then this pair of electron which is provided is purely from the ligand side. So this is how your metal ligand bond forms. This is how we discuss, and of course all these orbitals, they organize around the metal center in different ways. There are more than one, and then you have the formation of a certain structure. So it was successful in explaining the structure, no complaint about it. But again, as we have already realized in your chemical bonding chapter in your 11th class also, that it's very hard to say that any bond can be purely covalent. Very few and extreme cases can be there where you have the same kind of atom. Okay, for example, hydrogen, in molecule hydrogen, HH, same type of atom. Otherwise, wherever you have two different elemental atom, there is going to be difference in electronegativity to some extent, and therefore although they may be both, let's say, carbon and hydrogen, for example, even in carbon and hydrogen where you have both non-metals, we may say this is a covalent bond, but because of the difference in the electronegativity, carbon becomes partially negatively charged with respect to hydrogen. Hydrogen is partially positive, carbon can be partially negative. Or the scenario might change where carbon might be bonded, let's say, to halogen. Then halogen becomes partially negative and carbon becomes partially positive. So you can see that there are example already. We know that no bond can be regarded completely covalent. Sorry, covalent and completely ionic, because there is always an element of other type of property. For example, so here we consider in valence bond theory the bonding as a pure covalent bonding, but we realize that okay, it doesn't explain many things, so why not we try to adopt a little bit different approach, and let's see if that is successful. So this theory is based on considering the metal ligand bond now as ionic. This is ionic bond. In the similar manner, here we are regarding the metal and ligand bond ionic. One point that one can justify is because there is a metal. Metals are generally positive, positive, electropositive, and electropositive means they have got tendency to, they are electropositive and they can draw the negative charge to them. So in this consideration, what happens is we consider the metal center, whatever it is, a positive center. This metal center is regarded as a positive center, and the ligand which is going to form the bond is regarded as a negative center. This is the difference. Now you will see that how it is justified. So the thing is that the ligands which are already ionic in nature, they are anyway by default regarded as negative point center. See, I am using the term called point center. Please try to realize this. So it doesn't matter what ligand comes, what metal it is. We are simply considering the whole entity as charge center. This is important. Okay, because otherwise we will start discussing everything together, let's say size and everything, then we'll complicate the matter. So we are right now not considering metals identity too much or ligands identity too much. We are simply considering the charge. Please see, that's why I'm saying that we are considering this model as an electrostatic model, as if we are talking about in your physics the interaction between the charges, opposite or equal, right? Similarly here also we are talking about as if the metal and ligands are considered purely charges, charge points. Okay, So if it is an anionic ligand, for example, you know the anionic ligand like Cl, Br, all these, okay, SCN and anything, okay, all these are negative ligands. So negative ligands by default are regarded as negative point charge, okay. Now what about the neutral molecule? A neutral molecule like NH3 or water or CO, these molecules are regarded as, neutral molecules are regarded as if it is a dipole. So there is a negative center to dipole and there is a positive center to dipole. It's like a dipole. This is a dipole, okay. So when I say negative center, I'm not trying to separate the charge completely, but let's say partial separation of charge, minus delta plus delta, and that can be found across the molecule, right? So for example, in ammonia molecule, it is the nitrogen atom which should carry the minus delta side, right, minus charge side, and hydrogens can become positive. Similarly, in carbon monoxide also, you have oxygen forming the negative charge center and carbon should form the positive charge center. So these neutral molecules are regarded as point dipoles. This is called point dipole, like a dipole where charges are considered again as point without considering about the size. Please try to see the the idea of point here. We are less concerned about how much size and all those things they are occupying in space. It's just that we are considering the main effect due to the charges. So these are regarded as point dipole. But when it has to face the metal, it will be the negative point that will face the metal. That is something important, okay. So negative point of the dipole being pointed towards the metal, even if it is a neutral molecule. For example, if I have a metal which is a positive center, okay, and then if the ligand is like a dipole, okay, for example, so its negative center is oriented towards the metal, would be the positive center of the dipole. So that is how you have to regard a positive and the negative charge interaction. So this way we are mainly focused on this bonding between the interaction between this metal center, positive center, and then this negative center of the ligand dipole, okay. So I hope this is the basis. Let's say I have not yet done with the diving into the depth of the theory. This is the beginning, basic idea, which is different from your valence bond idea. The valence bond idea regards the covalent bonding nature, and this regards the ionic nature of the metal ligand bonding. Static. Now let's go a little bit more, expanding the metals structure. And you know that in all the coordination compounds, mostly the coordination compounds that you have in syllabus and in general, they are what? Transition metals, right? And transition metals outermost orbital has s, p and d orbitals, and you may have also realized the s, p orbitals are mostly filled. It is the d orbital generally that remains empty, partially empty. I'm saying it could be completely empty also, it could be partially empty also. So it is this orbital which plays a significant role, because s and p orbital here, they are regarded as, like, okay, one more thing that you can always consider is, I'm not talking about whether it is 3d, 4s, 4p, or let's say 4d, okay. So when we consider all these orbitals, okay, let's say these belong to one principal quantum number, the outermost, the d orbital, you remember that depending upon the nature of metal and the influence, this energy difference between them actually is not much, okay. If you look at the energy level diagram, then what happens is they become more or less similar in energy, and the electron can move around. That's what it is. But you remember one idea when we were discussing the atomic structure, which orbital are more deeply penetrated to the nucleus? Remember the penetration effect of orbitals, because it depends upon the shape of the orbital. So orbital is more penetrated, then p, then d. So for a given principal quantum number, or let's say for a given outermost shells, it will be the d orbital which will be the most outer also. Among the spd also, it will be the d orbital you can regard as most outer. And that means these orbitals should play primary role in the formation of this kind of interaction. So we are mainly focusing only on the d orbital. That's why This theory regards the d orbital as the primary player for the electrostatic interaction between the metal and ligand. Okay, so here is a penetration effect, and that's why this is the, even for a given principal quantum number, or let's say for a set of similar energy orbitals, the d orbital are primarily outermost. Okay, so then we focus only on the d orbital's role. Okay, now 5d orbital, you know the d orbital is a set of five orbitals. Okay, d, the group of any, whether you talk about 3d, so there are 3d orbital, 4ds orbital, any of those. Okay, any of these two will be playing the role, either this or this. So they are set of 5 orbital. Consider them first without worrying about ligand and all those things. Just consider an isolated. This is our starting point to regard what happens to the metal d orbital when you start your journey from considering it as a gaseous metal atom or ion, isolated. D orbital, let's start by considering the 5d orbital in the isolated gaseous metal atom have same energy. We know that, right? The dx, dy, dx square minus y square and dz square, all these orbitals are, they are same in energy. I hope this is visible to you. This is, I picked up this diagram from a book, dx square minus y square and then dz square. Okay, and then dx square. All of them have same energy. So here is an energy diagram which shows that, let's say in a free metal ion or atom, all the d orbitals are considered to be of the same energy. By the way, the diagram in your book that is given is like drawing the lines to show that. See, this causes a little confusion, because as if it seems that the 5d orbitals are of increasing energy, right? But actually in good diagrams, you will see that these orbitals are shown by like these kind of circle or boxes together at the same level of energy, like 5 orbitals are shown like this, or sometime in some of the books they will be shown like in the boxes like this, 5d orbitals, just like we have used them in the valence bond theory. So they are shown at the same level, so that you understand all the d orbitals have the same energy. Here there could be a confusion, but don't worry if you understand that all the d orbitals are put together and they are of the same energy in an isolated gaseous metal atom or ion. Think about even again. Okay, one more thing before we move further. There is a term which is used. You remember that whenever we say that all the orbitals of a certain principal quantum number, if they have the same energy, we call them as degenerate. Degenerate orbitals. Same energy means they are referred to as degenerate orbitals. Okay. Now again continue with the same metal atom or ion. But let's think about them. This metal atom or ion, we know that it's a positive center, but it also carries, okay, right now we are talking about the d orbital. The d orbital will be filled up with the electron, whether partially or let's say completely, doesn't matter. Some electron will be there, some electron density will be there, because empty orbital we don't consider, right? Either you consider 3d or 4d, you have to consider the with the electron, right? Whatever number they have. Okay, so these electrons, they are initially spread out in all the orbital. You know that you have to now picturize the simultaneously the quantum understanding of electron density. Otherwise, if you consider the point electron 1, 2 like that, then what will happen? You will consider them in this. That will not cause the understanding. Here, this is like a quantum mechanical model. So it takes the understanding that the electron density is spread, whatever number of electron you have. Okay, 5, 10, 2, whatever. So they are that, if the electron density is considered moving across, then only you can say that all the metal d orbitals are of equal energy. Okay, doesn't have to be all the orbital filled or completely empty, but even though there are few electrons, all the d orbitals are of equal energy, simply because the electrons are indiscriminable from their participation into various orbital. Okay, so that's what leads to degeneracy. Now if you surround this metal atom or ion with its d orbital carrying some electron with a spherically symmetric field of negative charge, Why, you may ask the question, why are we considering this? Well, we will translate this field slowly into ligand field, ligands, but we start with a very ideal situation. We start with the most ideal situation where your metal atom is free, completely free metal atom or ion. Okay, metal atom or ion, okay, depending upon the oxidation state in the complex. Then we regard this to be surrounded by a spherically symmetric field of negative charge. I have chosen negative charge because our ligands are going to provide the negative field. And then we start with that ideal situation and make it more complicated or more specific. So what happens? You know that now there will be a repulsion felt between the metal d orbital electron and this negative field of some charge. Okay. But we are considering that whatever charge you are considering, whatever magnitude you are considering for the charge, it is considered as if surrounding, it is like a fluid that is filling a certain kind of sphere around the metal. So it is equally distributed everywhere. And when you have equal distribution of this negative field, okay, the field due to negative charge around the metal, then all the d orbital electron, they will feel equal field from all. So that's why it's like a symmetric field we are considering. In that sense, you will not be disturbing the degeneracy of the d orbital. They will still remain equally in terms of energy, but their overall energy will be increased because now there is a certain kind of repulsion happening between the metal electron and the negative charge field. Whatever charge you have everywhere, it's like a fluid. I'm not trying to, okay, let me remove this. So there is a repulsion which is being felt by the electrons in the metal d orbital because of the electron, because of the negative charge field. So this lifts the energy. So here in the diagram you can see that we are showing all the 5d orbital which are little bit higher in energy than the original state. Whatever energy state you have here, compared to this energy state is higher, right? So they are lifted, their energy is lifted. So average energy of the d orbital in the spherical crystal field is now increased. Okay, and they are still degenerate. They are still degenerate because we have not done anything to remove the degeneracy. Because your all the electron in all the d orbital, they are still feeling equal field. Okay, as if the threat is equal everywhere. So their energy is increased but equally. So the important point that I am trying to emphasize again and again, the degeneracy is still maintained but overall energy is increased. Now we start by considering, think about that this field which you are initially starting as an ideal situation of a spherical field, consider that instead of this field being spherical, if it is the ligands they approach, okay, if the field is created because of the ligands, and you know that whenever the ligands are going to approach this metal atom or ion, they are not approaching from all the infinite directions, right? They are coming in very specific direction. For example, in octahedral complex, the 6 ligands will come in 6 directions. We will see that, okay? The 6 ligands will come in 6 directions. In tetrahedral complex, 4 ligands will come from 4 different directions. So the remaining portion, which is from where the ligands are not approaching, they will have little different effect compared to the directions from where the ligands are approaching. What will this do? Okay, here I'm saying that this will lead to a little different experience of repulsion by different orbitals. How? Let's look at this. Instead of considering the spherical field, let's consider a scenario in which now, if it is octahedral complex, the ligands will approach from 6 different directions, right? They will approach from 6 different directions in 3-dimensional array. It looks like a plane, but it's a 3-dimensional approach, correct? In 3 dimension. So it is not same spherically symmetric as this, because now the directions have become very specific for this negative charge approaching the metal, and then metal's d orbital wherever it is feeling this field. So what will happen? Those orbitals which are oriented or facing directly to these ligands, they will feel more repulsion, and those orbitals which are not facing these ligands directly, they will feel less repulsion. Naturally, there is a difference in the shape of the d orbital and the orientation, we know that, right? This is your d orbital diagram. Similarly, if you consider even the tetrahedral complex, the 4 ligands are approaching from 4 different directions in 3 dimensions. And here also you will realize when we discuss that the different d orbitals, different 5d orbital, they will feel different level of repulsion. Okay, and that will lead to a certain discrimination of energy, little bit difference in energy between the d orbital itself. So let's see, first let's consider a situation where we have octahedral complex. Let's start with octahedral coordination entity and see what happens to different d orbitals when 6 ligands, okay, octahedral means coordination number 6, that means 6 ligands should approach or 6 coordination bonds should form. Right now we are considering, let's say, monodentate ligand charges, okay. And then, so let's look at this diagram which suggests us the orientation of various d orbital. Look at these orbital dx square minus y square and dz square. Here we know very clearly that these are oriented along the axis. If you try to create a certain reference coordination system, then we can very easily say that if you align a complex in a way that the d orbitals are placed along this axis, we know that dx square minus y square and dz square, they align along the axis. But dxy, dxz and dxy, dyz, all these orbitals lie in between the axis. Right? Remember, just this is not clear here, but look at this one. Suppose we talk about dxy orbital. Then you consider this dxy orbital lying in between the x and y axis in the plane xy. This is a plane xy, you can see that, and dxy, dx and then y, they lie in between the axis, right? So this is the situation of 5d orbitals. Now what do you think in octahedral complex will happen? See, the ligands, as I said, we consider that whenever the octahedral complex is being formed, think about this situation. I have taken on the other page here. Here, this complex, when I place it in a like a box here, considering that this is our center, metal center, and these are ligands. So this can be considered in a cube where I consider the x-axis, y-axis. Let's say this is your x-axis, this is your y-axis, and the one which is coming out of this plane is z-axis. So if you consider this situation in octahedral complex, right, where your ligands are approaching these directions x, y, z from all the 6 directions, right? Okay, na? The ligands, 6 ligands will approach from 6 directions. So you can consider that now what will happen is, so the d orbital which are aligned along these axes, the dx square minus y square and dz square, they will feel more repulsion because of the ligands which are approaching from these directions, right? The blue dots are shown as a ligand only, although they are fixed here, but you can think of they are approaching initially to the metal center, and they approach along the directions where the dx square minus y square and dz square, okay, it doesn't matter, I have drawn it xyz, that's not very important. So they will feel more repulsion, and the orbital which are lying in between the axis, they are little bit off, so they feel less repulsion. I'm not saying they will feel no repulsion, but they will feel less repulsion. Now the thing is that how do you strategize, how do you design a strategy to consider the energy differences between the two type of orbital? This basically leads to the one set of orbital feeling more repulsion and the another set of orbital feeling less repulsion than this compared to these orbitals, okay, in the formation of octahedral complex. Okay, so what is the consequence of this? This has led to clear-cut splitting of d orbital. Remember, I was so far talking about all the d orbitals are degenerate until the ligand field was considered, until the field due to the ligands were considered. As long as I was considering the spherical field also, no problem, I can add more field to this. but then the degeneracy was not affected. All the d orbitals are behaving the same way. But when you consider the ligands approaching a fixed number of ligands in certain directions, specific directions, the degeneracy is now lifted. The degeneracy is now lifted. And the two, in very simple term, we can say that this set of 5d orbital is now splitted into two set of orbitals. Okay, I was mentioning here dx square minus y square and dz square, it forms one set. I will tell you that this set is referred to as EG in a original term of this theory. Okay, it is not randomly put. Very carefully, it has a meaning into this, which we can't discuss why it is like this. But this set is referred to as EG set, and this set is referred to as T2G set. Don't make capital T. It is small t, and the 2G T2G. 2G is a subscript. Okay, here also E is small and G is a subscript. You will see how this will differ in tetrahedral. So you have to be very careful you use right. That's why I'm saying children tend to mix. So I'm being very careful with you when I'm trying to tell you what meant for tetrahedral complexes. So dx square minus y square and dz square together is EG. We can even refer this set as a EG set, and right now this one as T2G set. Now please let's consider this one. In this diagram, energy level diagram, I told you that if you have a spherical field, then the overall energy is lifted from the isolated metal atoms energy, correct? No problem. Now when you are considering reducing this field into the ligands field due to the ligands, only due to the ligands, so specific direction, whatever repulsion that existed before between all the 5d orbital and this field, it should be same. Even here we are considering the same field, but what we have done is now we have uh, taken out this entire spherical field into the pockets like 6 pockets. We have made 6 pockets, and we have also realized that it is the dx square minus y square and dz square, they feel more repulsion, okay, because they face the ligands directly, है ना? So they are uplifted from this average energy. Their energy is increased with respect to this average energy, and the other orbital's energy is with respect to this average energy is decreased. If someone is gaining in that house, other has to lose. It's like that. So what I'm trying to say is that, let's say initially I gave let's say 100 rupees to a class of 5 children. These are 5 children here, okay. Now I considered that all the children are equal, so that's how I gave. So if you consider all of them getting equal, then everybody should get 20 rupees. But suppose if I have to still distribute the 100 rupees to 5, and if one is getting 30 rupees, then somewhere there is a loss, right? Some other child has to lose. That's what is happening here, okay. So if you consider that this same field is now considered to be felt differently by all the d orbital, some orbital will gain energy because of experiencing higher repulsion, e.g. the other orbitals will then feel a little bit less than the average what they were if it was spherically symmetric field. Okay, did you get this point here? This kind of splitting that has happened between the d orbitals into two sets, one is Eg and another is T2G. Please see, in octahedral complex it is the T2G set, this set which has gone down in energy, and Eg set which has raised in energy. So this splitting is referred to as crystal field splitting. Crystal field splitting. By the way, why we are calling this whole thing as crystal? You remember whenever you discuss the ionic compounds, it is the crystal, right? The ionic interactions are in solid crystals. They are discussed as if the interactions are equally in all the directions, right? So that's why crystal field, it is the crystallized field. Think about that. The field interacting, field between the positive and negative charges. It's like that. So this splitting of energy has happened, or actually speaking, it is the splitting of 5d orbitals into two groups. One is Eg, another is T2. Now the question is, how do you account these? Think about this. you may have different magnitude. We can actually find out. There is this problem remains the problem of spectroscopy, which is going to come up in tomorrow's class. But right now, just to account here itself, let's say our next reference point, forget about this isolated case because that's not important. Our real situation starts from here. This should become our reference point for energy now, potential energy, right? You can start potential energy consideration anywhere. So if I consider this average energy here, this average energy, if I regard as zero energy, think about this. This center here, this center is regarded as zero energy. Okay, of course, there is an energy here, but I could have chosen this as 0. But I said that potential energy reference you can change depending upon what system you are considering. So this is good to start to understand, but our starting point is this. So this is our zero center, zero energy. From here, suppose if you consider, then how is the difference between these two orbitals is to be regarded. So this center is referred to as, this is a name to this, it's called as barycenter. This center is referred to as barycenter. And the difference of energy between the d orbital, so you know that some orbitals have lowered energy, some have increased the energy. This difference of energy is called as crystal field splitting energy. It is symbolized by delta O. In tetrahedral, it will be symbolized by delta T. So remember the difference. When you say O, O is reserved for octahedral. Okay, so don't mix up again. So this energy difference, overall energy difference, is called as delta O. What I am trying to write here is the energy difference between T2G and EG. Okay, is referred to as delta O. This is called crystal field splitting energy. Okay, sometime CFSE orbitals. And the sum of total energy of all the d orbitals, including both of T2G and EG type, at the barycenter should be equal to 0. And that can be very easily achieved if you simply partition this delta O into 3 by 5 delta O multiplied by 2, which is the weighting factor or weighing factor of EG orbital, and 2 by 5 delta O with the weighing factor of 3. So this ensures the sum of all the energies of all the orbitals at the barycenter equals to 0. And obviously we understand that the value of delta O should sum up from these fractions of 3 by 5 delta O and 2 by 5 delta O to delta O value. Okay, after realizing the possibility of having the crystal field splitting due to the field of ligand, now is the time to realize what all the factors that will affect the value of delta or the crystal field splitting energy. So the two important factors that will primarily affect the value of delta O is, first is the field that is produced due to the ligand, or indirect we were saying that it's the nature of ligand. Second factor that will also affect is the metal ions electronic configuration, or we can say is the type of metal ion that is present at the center. Now suppose, in order to understand the effect of ligand, which ligand will cause how much of splitting, one can do a very simple experiment in which, suppose one has ended up preparing a series of complex compound. Just for simplicity, let's take octahedral complexes of a certain metal where metal is fixed. Okay, say for example your metal is fixed, and now you create a series of complexes with various types of ligand and try to figure out the value of this crystal field splitting energy into various kind of complexes through these ligands. Then it seems that different ligands, they arrange in this increasing order of their the ability to cause the crystal field splitting. So this makes the conclusion, or let's say this makes a certain arrangement of ligands in a certain series. This increasing order of field strength into this series is referred to as a spectrochemical series. Here certain set of ligands have been shown as or they have been deliberately called as weak field ligands, versus the other set of ligand which are referred to as strong field ligands. Of course, there is a systematic change or the increase in the ability to cause the crystal field splitting, but relatively this set of ligands will cause lesser of splitting compared to this set of ligands. Okay, this. Now let's look at how to achieve various electronic configuration in various types of metals under various kind of field that are produced by the ligand, whether it is weak field ligand or the strong field ligand. Because if your metal has an electronic configuration of d1, that means there is only one electron to be considered to be arranging into this 5d orbitals. So how will you arrange if there is an octahedral complex of um, with the electronic configuration of d1 type? Okay, so naturally in the complex you will have the two set of orbitals that are first of all created. One is Eg and another is T2g. So this is the Eg group and this is the T2g group, and the energy separation of course is, let's say, delta O. Now since there is only one electron here, this one electron will obviously be occupying the most the ground state, okay, because there is one electron only, and one can fill here according to Hund's rule in the lower T2g orbital. So the electronic configuration for the metals D electronic configuration in this octahedral complex is simply can be written down as T2g1 Eg0. Okay, it is understandable. And similar thing will happen for D2 electronic configuration, where both the electrons will be in the lower T2g orbitals, and the electronic configuration for D2 type of metal electronic configuration in the complex will be T2g2 Eg0, and the similar thing will go on up to D3 electronic configuration. And here the rule of filling the electronic configuration, which is Hund's rule, is completely obeyed, and here you have T2g3 Eg0, and all these three electrons will remain unpaired in three different d orbitals. But then the question arises, what should happen if the electronic configuration or in the d electronic configuration of a certain octahedral complex is d4, like this? So let's take the example. Now here situation depends upon the magnitude of delta O also, okay, and that purely depends upon right now the type of ligands that is gone in the formation of the complex. For example, let's consider this MnCl6 3-, this is one complex where Cl is a weak field ligand. It belongs to the group of weak field ligand. We can see here Cl is like a weak field ligand, and there is another complex of manganese which I have chosen here with the cyanide ligand that belongs to strong field ligand. So let's see how to write down the d electronic configuration of the metal in these octahedral complexes. To start with, we always first consider the metals oxidation number first in the given complexes, and you can see here very easily in both the complexes the metal is with the oxidation number of 3+, because in both the cases one can calculate very easily is 3+, and therefore the electronic configuration for Mn3+ is 3d4, because Mn has electronic configuration of 3d5 4s2, 3 electrons gone, so it has become 3d4. So let's first consider the electronic arrangement of these 4 electrons in the d orbital in this complex, which is formed with the weak field ligand Cl. Okay, so let's consider the complex with the weak field ligand, which is MnCl6 3-. Now please see here, we are keeping the nature of the metal same, so it will be only whatever electronic configuration that we are going to achieve is purely determined by the nature of ligand, one causing a strong field versus the another causing the weak field. Now let's look at here in the weak field ligand. So d4 is the electronic configuration. So here you have 4 electrons in the d orbital. So if you first arrange the 3 electron, they will definitely go as single electrons in each orbital, of T2G group. But then where should I fill the fourth electron? According to Hund's rule, it should, if you remember, the Hund's rule said that once all the degenerate orbitals are filled singly, then the pairing of electrons should happen. So here, next electron could have been, pairing up and making one electron pair. But then there is another factor which also determines this pairing of electron. There is something called as pairing energy, which is the energy which an electron actually feels. Electron actually has to, pay off to pair up with another electron. So whenever in the same orbital the two electrons pair up, okay, a certain amount of energy is required to pair them up, and that energy is referred to as pairing energy. Now this is an extra energy which is required to pair the electron. First of all, you should ask the question, from where does it arise? Well, one can think of the two electrons are actually have a rippling effect on each other. So naturally, but they require certain amount of energy to pair them up, and that energy has to be provided extra. So that is called pairing energy. Okay. But then one may also ask the question, if they are rippling each other, then what is it that is making them paired up at the first place? In the sense that there is a requirement by the spin property. Okay, when the two electrons are pairing up, first of all, please see they are pairing up with the opposite spin. So a spin property requirement pairing up with the opposite spin, and that is what is causing them to pair up. And if the pairing energy here is greater than delta O, value of crystal field splitting. So it is much easier for the electron to actually remain unpaired in the higher orbital of EG group, and that's how the electronic configuration is achieved in this way. So it is EG group. So the electronic configuration that is achieved for the metals d orbitals in this complex can be written down as T2G3 Eg1. This is the kind of electronic distribution which was earlier just D4 we were writing, now can be written down in the complex as T2G3 Eg1. You may ask the question, why we have to really consider this? Well, first of all your spectroscopic property will be determined by the way in which the electrons are distributed in these two set of orbitals. The kind of electronic transition that will happen by absorption of energy depends upon which electron is where, and of course on the separation of energy. So it is this electronic configuration that is needed to be understood first, and also of course complex. For example, if I take the complex compound which is MnCN6 3-, where cyanide will cause a strong field, and then what happens? So in this complex, the separation delta O, which is called because of cyanide ligand, which is a strong field ligand, is so enormous that it is much higher than the pairing energy. Okay, the same pairing energy which I just discussed here, which is required for the electron to pair up with pre-existing electron in the same orbital. So this delta O is much higher than pairing energy. That means electron can be easily paired up in the lower orbital itself, then going to the higher energy orbital. See, both require the energy for the electron to be pairing up or to be sent up to the higher orbital. But then which one is lower, that will determine the electronic configuration. So in this case, when you have a strong field ligand, all the electrons now tend to be first singly filled in the lower orbital, then also should be paired up in the lower orbital itself, and then the next electron should go to higher orbital. So here you have T2G, electronic configuration will now be written down as T2G4 Eg0. That means there is no electron in the higher orbital. So this is how one can write down the electronic arrangement or electronic configuration of the central metal in a complex compound, depending upon the kind of ligand that has gone into the formation of the complex compound. Now one can apply the same idea by consideration of strong field versus weak field to write down the electronic configuration of, let's say, even D5. If it is strong field ligand, here is the example. For example, okay, if it is a weak field ligand, for example, FeF6 3-, where F is a weak field ligand, the electronic configuration is like T2G3 Eg2, where all the orbitals are first, even including the higher Eg, are first singly filled, and then the pairing should be followed if there are extra electrons. So D5 will only have this electronic configuration. In case of strong field ligand, it should be T2G5 Eg0. Similarly, if you go, so these are the examples here, real example of the complex compound where you have the same metal and different the ligands with the different field of strength. Similarly, for D6, the electronic configuration in the weak field ligands case will be T2G4 Eg2, because now you have first filled all the T2G and Eg singly, means with one electron, and then the extra electron now first start pairing up in the lower T2G. But in case of D6 electronic configuration in the strong field ligand, which is like this in this complex, you still have to first complete all the orbitals in the lower T2G, and then only if you have extra electron after filling all the T2G completely, then it should have moved to the Eg. But here you have 6 electrons, so they should completely fill only lower T2G orbital, and therefore you have T2G6 Eg0. So please keep noting the kind of changes or differences that the electronic configurations have if the same metal is formed with the weak field ligand versus the strong field ligand. So here is a cobalt forming complex compound with Cl, which is a weak field ligand. It gives this electronic configuration of the metal, and here cobalt forming complex with the ammonia, it gives this kind of electronic configuration in the octahedral complex. One can also consider the similar manner the D7 electronic configuration. But then if you go for D8 and D9, now you will have sufficient number of electrons to first completely fill all the lower T2G orbital, whether it is a strong field or weak field. Okay, because now the number of electrons, they have exceeded the required number to be first completed in the lower T2G, and also the singly each of Eg orbital. So you first fill all the orbitals completely in the lower T2G, and also single electron filling each orbital in the Eg. So it doesn't matter whether now you have a strong field ligand or weak field ligand, the electronic configuration remains the same. Similar goes for D9, but then you are just considering the addition of one more electron in the Eg orbit. Okay, so this is how one can write down the electronic arrangement in various type of complexes with the different metal electronic configuration, considering the strong field versus the weak field ligands. And mind you, all this information or the understanding will be useful in order to exactly predict the color of the complex compound and other properties, of course. So the electronic, just writing down electronic configuration in weak field versus strong field is not the kind of target, but actually we want to explain various properties of the complex compound by using these electronic configuration once we have established them by using crystal field theory. And now let's understand how this theory actually helps to overcome various limitations which were there with the valence bond theory of value. So variety of properties can be exactly predicted about the complex compound or explained properly. For example, the color of the complex compound, very important property. Color of the complex compound we can explain very nicely now and accurately by using this theory, because the electron now, because this delta O is related a certain to a certain absorption, certain wavelength, certain frequency, and hence certain wavelength. We know that. We will understand this a little bit later, but the color of the complex can be very easily explained due to the electronic transition for the electron from T2G to Eg higher orbital by the absorption of light or energy in general. Second important factor is now we can also predict exactly the magnetic property of a complex compound, if it is a weak field or strong field. Again, by considering the example value of the same metal. Please see here these two examples, MnCN63- and MnCl62-. One is in the strong field ligand, another is in the weak field ligand. Now we know that in the strong field ligand, for Mn, now we just took the example of manganese, and here it is a D4 electronic configuration. D4 electronic configuration here. So D4 electronic configuration in the strong field ligand, it is like this. Here you can see in T2G orbital there are two electrons which are unpaired. But if it is weak field ligand, then all the electrons are unpaired. So 4 electrons are unpaired if it is MnCl6 3 minus, and only 2 electrons are unpaired if it is MnCl6 3 minus. That means the magnetic property of this complex will be equivalent to the 2 unpaired electrons, because the magnetism arises because of the unpaired electron in a metal complex. Similarly, the magnetic property of this will be due to the 4 unpaired electrons. So this complex will be much more paramagnetic than this complex compound, and that can be exactly predicted and experimentally verified also. So the magnetic property or paramagnetism for this complex corresponds to this magnetic moment value, which is calculated by using this formula here. Magnetic moment is related to the number of unpaired electron in the given complex compound, n into n plus 2 square root of this, and Bohr magneton is the unit of this. So 2 unpaired electron for this complex compound, this will be the value, and 4 unpaired electron, n is equal to 4, then this will be the value, and this comes exactly with the experimental results also. So this, okay, so variety of limitations that we had with the valence bond theory have now overcome in the crystal field. Now, after having understood the crystal field splitting in octahedral complex, now is the time to realize the same thing, let's say in tetrahedral complex also, or the complexes with the coordination number 4. Okay, so there will be slight differences that we have to appreciate, and we will understand them here by using these diagrams. So just recall please, in case of octahedral complexes which we have just discussed here, here in case of octahedral complexes, we realize that the 5 degenerate d orbitals, if we consider them in a spherically symmetric field of negative charge, then if the same field is now reduced to the field of 6 ligands, then the d orbital separated into the 2 groups of orbitals, the Eg with the higher energy compared to the lower energy group of orbitals T2g, and the T2g is a group of dxy divided dxz, and the higher energy group is comprised of the orbitals dx square minus y square and dz square. And this was explained, if you remember, because in the formation of octahedral complex, when all the ligands are approaching the metal center from 6 different directions, in this diagram, if you consider that the ligand are approaching along the center of the faces of this cube, that means along x, y, z directions, okay, both from plus and the minus direction, that means opposite directions. So 6 ligands will approach along the center of the 6 faces towards the metal, and in doing so they actually encounter these 2 orbitals directly, the d orbitals directly, that means dx square minus y square, which is also aligned along the x and y axis, and dz square, which is aligned along the z axis, while the other orbital, they are not along the axis but in between the axis. For example, if you consider this dxy orbital, this is in between the x and y axis. The lobes of the d orbitals are represented here in between the x and y orbitals. So the ligand which is approaching along the x or the y direction, that will feel more of repulsion from the orbitals which are along the x and y axis, which is dx square minus y square, but it will feel less repulsion compared to the orbitals which are in between the axis. And so all these 3 different orbitals which have their d orbital lobes in between the axis, they will cause less repulsion to the approaching ligand compared to this set of orbitals. So that was used, this whole idea was used to explain the kind of separation of the degenerate orbitals that we achieve in case of octahedral complex, and leading to e.g. this means the dx square minus y square and dz square higher orbitals, and T2g group, which is another 3 orbitals at the lower. And we explain all these things, like how one can actually consider the separation of the overall separation between the two groups. Well, what happens? Let's see what happens in case of tetrahedral complex. Now the scenario is a little different here. If you first consider a tetrahedral complex in the similar kind of cubical arrangement by considering the metal at the center of the cube, and then to arrange the tetrahedral complex you have to consider the ligands at the diagonally opposite corners of the cube. So for example, you have 4 ligands and they are represented here at diagonally opposite corners of the cube. Okay, two at the top and 2 at the bottom in a different direction. So the ligands now will approach to the metal in this diagram or in this reference frame along these directions. This is like so cubic. Imagining a complex compound in the cube is only a kind of creating a reference, so that we have a same reference to be considered for the arrangement of the d orbitals of the metal center, and also the approach or the arrangement of the ligands. Okay, so if I choose the same frame of reference of x, y, z orbitals, axes, and then these axes are represented along the center of the faces of the cube. Metal is at the center. So now please consider the way in which the ligands are approaching the metal center. And if you look at here carefully, the ligands are approaching, while the ligands are approaching to the metal, they are not approaching along the axis. Unlike the previous case of octahedral complex, where the ligand actually approach along the axis directly facing these orbitals low, but now they are approaching at a certain angle. So that means they will feel more repulsion due to the other orbitals which are in between the axis. So we are not saying that these orbitals are facing these ligands direct. There is a certain angular difference, but still they will be more in the close vicinity. These ligands will be in the more closer vicinity to the orbitals which are in between the axis compared to the orbitals which are along the axis. And in doing so, we can think of very easily that these ligands in the tetrahedral complex will feel more repulsion due to these 3 set of orbitals, and less repulsion due to these 2 set of orbitals. So the scenario is reversed compared to what we have discussed in case of octahedral complex. In case of octahedral complex, it was this set of orbital which was feeling more repulsion, and this set of orbital was feeling less repulsion. But now in case of tetrahedral complex, this set of orbital, the 3 orbitals, similar orbitals, that is feeling more repulsion because it is in between the axis and the ligands are also not approaching directly along the axis, while the other 2 orbitals or the other set of orbitals, it feels little bit less repulsion compared to the other 3. Okay, so now the scenario is completely reversed. And as I said in the previous discussion also for octahedral, here also we will bunch up this set of orbitals into a group and we will call it as T2 set. Now the terminology come from the consideration of the quantum mechanical treatment, but which is out of scope to be discussed here, and spectroscopic property. So we are just accepting these terms here, and this set of orbital dx square minus y square and dz square is referred to as E set. Now also consider the difference between the way in which we named in octahedral, we called their T2g and EG set. Right now we are simply calling them as T2 and E set. So this should be clear. Okay, so these are the 2 set of orbitals or the 2 set of orbitals that will be separated from the degenerate state of all the d orbitals in a spherical symmetric field. Earlier, if you consider only the spherical symmetric field equivalent to the 4 ligands, then all the d orbitals are still degenerate. Of course, they are raised in energy compared to if there were no field around the metal, but then they are still degenerate. But when you consider the same field, spherical field, to be reduced to the field of 4 ligands now, just like we considered in the case of octahedral complex, in the formation of this octahedral complex, we considered this symmetric spherical field to be reduced to the equivalent field of 6 ligand. Then it becomes very specifically pointed in terms of direction, while here it is everywhere. So all the d orbitals are facing equal repulsion. But here the directionality of approach of ligand will cause the separation of two orbitals. Similarly, in the tetrahedral complex also, as we have just discussed, the two set of orbitals are separated, and here we have just realized that this group of orbitals will be raised in energy with respect to this reference point, which we refer to as barycenter here again. Okay, this reference center is referred to as barycenter. Okay, just like we talked about the barycenter in case of octahedral complex here. Okay, in the similar manner, this is barycenter where we are assigning the value of energy as 0, and with respect to this center, now we can say that the the T2 set of orbital is raised in energy with respect to this barycenter, and each of these orbitals are raised by 40% or 0.4 delta O, which is 2 by 5 delta, sorry, not delta O, now we have delta T. The T subscript comes because now this is a tetrahedral complex. In octahedral complex, we use the symbol delta O. Now we are using symbol delta T to depict this separation of energy, or this separation of energy which is called as crystal field splitting energy again, but now in this case in tetrahedral. In tetrahedral, we are talking right now the tetrahedral complexes where you have the 4 ligands attached to the metal. So this is the kind of separation we will have. 40% of delta T, that should be represented taken by each of the each of the T2 orbitals, and 60% of this delta T by each of the orbitals which belong to E group. In that sense, if we do weighted average now, considering how many of the E orbitals that we have, that means 2, and each takes the share of 60% of delta T, and 3 of the T2 type, and each takes the share of 40% of delta T. And if we sum them up, okay, considering the sign, of course, where we are considering the sign negative for the reduced energy with respect to this barycenter, then all of them, this energy should sum up to 0. Because please see why we are writing this negative sign for this contribution of energy, because if somewhere the energy of few orbitals has increased, that must be compensated by decreasing the energy of, by considering the decreased energy of other orbitals, and all this being considered with respect to barycenter, which has been assigned the value of 0 energy. If it was not the barycenter reference, this one, then all of them have increased the energy. Okay, so this same thing we have explained in your octahedral complex, so please consider that way. And of course, the 40% of delta T and 60% of delta T should amount to the total of delta T, which is the crystal field splitting energy between these T2 and E set. Now, after realizing this about the separation of orbitals, d orbitals in tetrahedral complexes, there is one interesting fact that also comes up, and it suggests that suppose if we happen to create two type of complexes, one is tetrahedral and one is octahedral, which is comprised of, let's say, the same metal and same type of ligand. In that sense, we can still say that the metal ligand bond strengths are approximately similar. Just that in one case you have 4 ligands attached to the metal, in one case you have 6 ligands attached to the metal, and of course the geometries are completely different. So this should lead to a separation of delta T, and this should lead to the separation of two type of orbitals as delta O. Now if we measure these in these two hypothetical complexes, okay, let's say we do the calculation, and we establish that we realize that the delta T is approximately 4 by 9 times less than delta O. That means delta O is much higher than delta T. Okay, even if you're considering same type of ligand and same type of metal, that means making all the factors irrelevant except the separation in the and the separation depending upon the whether it is an octahedral complex, or it is a tetrahedral complex. So in that sense we realize that this is how the values of delta T and delta O relate, and this delta T value generally in case of tetrahedral complexes is so small that it is normally found to be much less than the pairing energy most of the time, whether you have a strong field ligand forming a tetrahedral complex or a weak field ligand forming a tetrahedral complex. It so happens that the pairing energy always exceeds the crystal field splitting energy in tetrahedral complexes. Okay, so this relation generally holds either either in case of either weak field ligand situation or strong field ligand situation. Okay, so this is something that is different from octahedral complexes, because your delta T in case of tetrahedral complexes is sufficiently smaller value than the pairing energy of electrons. Okay, and therefore what happens is the whenever we write the electronic configuration, for example in a certain octahedral complex, oh sorry, in a certain tetrahedral complex, suppose the metal displays the electronic configuration of D4. Then how do we write the electronic configuration in the complex? One can think of just by considering the previous situation, that whether it should be Eg2 or T2G2 or T22, because here we have two orbitals in the lower energy, then the three orbitals. So first, one can consider this scenario if it was weak field ligand, and one may have thought of considering this scenario if it was a strong field ligand, where you first pair up the electrons in the lower energy itself. But this is not applied, because in any scenario, whether it is a strong field ligand or weak field ligand, your delta T is always less than pairing energy. So all the electrons tend to first singly occupy all the orbitals E and T2 type. That means all the electrons first cause a situation where you have high spin configuration. So in case of D4, the electronic configuration will always be E2 and T22, whether it is a weak field or strong field. Similarly, if it is a D5 electronic configuration, you can consider the electronic arrangement like this. And then on, suppose in a complex compound, if you have higher electron like this, higher number of electron like 6, then you can start considering them to be paired up first in the lower energy. So suppose if I had to write down the electronic configuration here for D6 in octahedral, then it should be 1, 2, 3, 4, 5 and then 6. Likewise, if you have more electron, then now we can continue pairing here, then here, then here, then here. So the electronic configuration here is like E3, 2, 3. Okay, so this is how one can consider the electronic configuration, and all these understanding match well, again let me tell you, exactly with the spectroscopic measurements of crystal field splitting. Okay, because they relate with this electronic configuration and this understanding that delta T is always less than pairing energy in case of tetrahedral complexes. So with this theory, again we are able to explain most of the properties which we were not able to explain by using valence bond theory for tetrahedral complexes also successfully. Okay.